Hello, and welcome to our presentation on New Clean Energy Sources and Storage Technologies for Design and Innovation 2020. This presentation is presented by Wai-Hang Chang, Patrick Hickman, myself, Yanao Lee, Suing Wayne, and Benjamin Whiting. The purpose of this presentation is to summarize our findings for new clean energy sources and storage technologies. We'll begin by giving a brief overview of Australia's current energy outlook and why research into this field is necessary. A list of project requirements will then be identified based on the needs of the Australian government. This will then lead on to a discussion on the performance criteria that were selected for this project, which were ultimately used to compare and contrast different design options. Although several solutions were considered in this project, only one of them was chosen for further investigation. In 2019, 79% of Australia's energy was produced using fossil fuels, which have many drawbacks, including causing climate change and being exhausting. Solar energy generation has seen a growth of 23% in 2019, and renewables in general provide 17% of Australia's energy production. However, renewable energy sources also have their own drawbacks, which have limited their use. For example, large-scale development of solar panels can be expensive, and they only generate power during the day. This unreliability can potentially be resolved using an energy storage system. Our project is to investigate the criteria for such a storage system and find a design that would meet these criteria. The following is a list of project requirements as specified by the Australian government. First, the solution must be capable of providing Australia with a source of energy, whether it be through energy storage or production or both. The solution must also have a minimal impact on the environment and should not contribute to carbon emissions. The solution must also be cost-effective, as it will make it a more desirable option for investors. In addition to this, the solution must also be capable of sustaining the country for extended durations. These project requirements were used to construct a set of performance criteria to evaluate and compare different design options.
The designs were scored against 5 criteria: scalability, cost, effectiveness, dependability, sustainability, and environmental impact. The 3 most important criteria are cost effectiveness, dependability, and sustainability. This is because for a design to be practical, it must also be affordable. The dependability and sustainability are also critical parts of the design, as the design must be able to dependably provide power and must be able to do so for generations to come. Finally, the design should have a low environmental impact and should be able to be scaled up in the case of future investment. Scalability is used to identify the amount of usable electricity that the design can export. The score levels represent major energy sources that we can provide electricity around Australia. When a design product can replace an energy source, it represents a leap in importance. This criterion is a staple for this project, as we need some way of ranking designs based on the amount of energy they can generate. That being said, this requirement is only given a weighting of 10%, as designs that cannot be scaled up to produce enough energy to significantly reduce the use of fossil fuels will limit possible investments. This criterion evaluates whether the design is cost-effective, which is scored into 3 parts: having market competitiveness, not having market competitiveness, and requiring government funding. The grading of cost-effectiveness is based on the price per kilowatt hour at peak in Australia. Although the government's focus is on new, low-polluting energy sources that do not rely on fossil energy, the solution must be cost-effective in some manner for it to be feasible and see implementation. For this reason, cost effectiveness was given 25% of the total weighting of the performance criteria. This requirement determines whether the design can reliably output electricity during operation. Solutions that receive the maximum score for dependability should be able to generate the exact amount of electricity required for daily demand. On the other hand, solutions that have a highly fluctuant energy output will receive a score of 0 for this requirement. Although dependability was not explicitly required by the Australian government, it was deemed to be a crucial component of energy sources and storage devices, as solutions that do not adequately meet this criterion are not likely to see any implementation. As such, dependability was given 25% of the total weighting of the system requirements. This requirement evaluates the duration that a design can produce sustainable energy. A design's sustainability is dependent on the amount of materials needed to operate the system and how abundant these materials are. This is then measured with respect to the amount of time remaining for fossil fuels. This requirement was explicitly listed by the Australian government as a priority for energy sources, and as such, it was given a 25% weighting of the total requirements. The environmental impacts requirement measures the amount of pollution to the environment that is generated as a result of using a particular design. For this requirement, the recycle rate of potential designs will be evaluated and compared against the recycle rate of solar panels. This requirement was chosen because reduced emissions is at the forefront of Australia's government's research priorities when it comes to energy sources. Overall, this solution was given a 15% of the total weighting for the performance criteria.
In this project, 3 designs for an energy source were proposed and evaluated against the performance criteria stated earlier. These designs were a hydrogen storage system, a marine tidal current energy system, and a compressed air energy storage unit. The design that performed the best according to the performance criteria was the compressed air energy storage unit. As such, this system was considered as the design that the best addresses the Australian government's energy priorities. For the next slide, advanced compressed air energy storage uses electricity to run a compressor, producing heated compressor air. Heat is extracted from the air and kept inside a thermal store, preserving the energy for later use. Hydrostatic pressure focuses air to the surface, where it is recombined with the stored heat and expanded through a turbine to generate electricity on demand. In this part, the business model of the compressed air storage is to buy power during off-peak and sell the power during on-peak. Solar power currently generates roughly 3.1% of Australia's energy demand, but could provide up to 7.9%. This would allow for the purchase of up to 9,000 gigawatt hour of electricity. In 2020 years, 23,000 gigawatt hour of energy was sold at over $5,000 per megawatt hour, according to the Australian Energy Regulator. Even though solar power costs around $0.12 dollar per kilowatt hour, it is likely that the power would have to be processed through a retailer at around $0.25 per kilowatt hour. The energy efficiency of the compressed air storage system is 60%. So the energy bought would have to increase by a factor of 1.67, bringing the cost to $0.41 per kilowatt hour. Selling this at peak demand would earn $4.58 per kilowatt hour. The system is orderable at only 55 decibel as the seat parameter, which is equivalent to the noise produced by a household refrigerator. This, in addition to the low maintenance requirements, makes the system extremely suitable for use in residential areas. The system uses underground tanks in order to store compressed air, and as such requires only a small above-ground footprint, up to 60 acres for the biggest facilities. Before implementing the compressed air energy storage system, the ethical considerations of this design must be examined. First off, it is crucial that all potential customers and stakeholders are made aware of this design's life cycle, costs, benefits, and drawbacks prior to investment. This ensures that all personnel involved in the design, construction, and maintenance of the compressed air energy storage system maintain and promote integrity in accordance with the Energy Australia Code of Ethics. This design should also promote sustainability, although it produces no emissions. A substantial amount of water and air may be needed to operate the compressed air energy storage system. As such, depending on the size and scope of this device, it is important that correct measures are put in place to minimize the environmental impact of this system. Thus, it may be necessary to steer off the design from the surrounding ecosystem and ensure that any natural resource consumed are properly preserved.
Hello everyone, I'm Zhiren Wang. Now I'm going to talk about the environmental factors of compressed air energy storage. Compressed air energy storage system only produce carbon dioxide and heat when they operate. Although the influent emissions are a problem, but this can be addressed by technology. The heat generated by compressed air requires water to cool it, and the way this water is treated is a problem. But the air is nearly infinite, so it has little impact on natural resources. Now is the conclusion of our presentation. Australia is over-dependent on coal, and the new resources of energy are on the horizon. For the presentation, we discussed hydrogen energy system, marine tidal current energy system, and compressed air energy storage in terms of environmental, sustainability, cost, and other aspects of Australian electricity. And finally, we chose compressed air energy storage. We also had a serious discuss on about business models, social issues, ethics, and environmental impacts. Finally, we conclude that air compressed energy storage is reliable and is indeed the best terms of environmental impacts and society. The cost to buy and store power for compressed air energy system is $0.41 per kilowatt hour, and this power can be sold by $5 per kilowatt hour, and it has the least impact on the environmental, so we choose the compressed air energy storage. Here is the references of our presentation, and here is the credits of every team member. Thank you everyone. Our presentation is over.